So in this video, I introduce various numerical methods to approximate definite integrals. Our typical integration techniques can fail to provide antiderivatives. So for example, if I want to know the value of this definite integral, I would need to know the antiderivative of the cosine of x cubed, and our techniques would fail in finding one for us. Well, but for definite integrals, we could still appeal to the definition and approximate that definite integral by a Riemann sum. The thing is, though, is that would still require quite a number of computations, and there might be a significant error at the end. So our goal is to find another way to numerically estimate our definite integrals, but try to keep the same number or so of computations. The first of these new methods is called the trapezoidal rule. Let's suppose we have the function f that is continuous on the interval from a to b. Further assume that its graph is always above the x-axis, so the function is positive over this interval. That way, the value of the definite integral of the function f of x, when you integrate it with respect to x, from x equals a to x equals b, is just the value of the area of that region beneath the curve and above the interval. Well, then, as we would have done before with Riemann sums, let's just form a partition of the interval from a to b, x sub 0, x sub 1, up to x sub n, which breaks the interval into n pieces. We'll assume that they're all equally distant, so that we'll have a common change of x, which therefore has to be the overall length of the interval broken up into the n pieces. Further, for each of these x values, go ahead and evaluate the function, and we'll call y sub I to be the value of the function at x sub I. And I've put in these horizontal distances that you can see. Please focus in on the kth such interval. When you do so, notice that I've highlighted a line segment on the graph. That's connecting 2 points of the graph. Those 2 points are the points whose x values are x sub k and x sub k minus 1. This one line segment will approximate the overall variation in the function over this interval better than any previous choice I would have used with a Riemann sum. Because with a Riemann sum, we normally pick an x value, and that determines a height. And if you remember, that height corresponds to a horizontal line, but no horizontal line will approximate this particular function over this interval, not very well at least. So this straight line segment will do a better job. Let's just find the area then beneath that one line segment and above the x-axis over this interval. When you do so, you wind up forming that particular trapezoid. The width of the trapezoid is the change of x, that's the distance between the two parallel bases, and the two bases in length wind up being y sub k and y sub k minus 1. So we can easily find the area of that trapezoid, which would then be the distance between the two bases, that's the change of x, and you would multiply it by the average of the bases. So that'd be y sub k minus 1 plus y sub k divided by 2. And all I did was put the division by 2 out front. Just do this now for every single interval. For every interval, we'll generate a trapezoid, we'll find the area of it, and we'll just take the sum of all of them. So if you want to approximate that definite integral, just use that the area, which is this definite integral, is about equal to the sum of the areas of all these trapezoids, and that's the summation as you see there. Notice what happens though when you evaluate this when k is 1 or k is 2 or k is 3. They all are multiplications, so it's a sum of products, but each one has the change of x over 2 as a common factor. So if you were to mentally take that out, all you'd have left is a bunch of y values being added together. Also notice that if you use k as 1, the very first part of the sum would be y sub 0 plus y sub 1. And there actually is no other way to get a y sub 0 in the entire sum. The same can be said for y sub k. If k is n, then y sub n only appears once in the entire sum. Every other y value will occur twice in the sum. Once for the summation, the portion of the summation in front, and then another in later the very next term. So for example, y sub 2 would occur twice. Once when you use k as 2, and once when you use k as 3. For that reason, we can rewrite that summation as this particular summation. It's the summation where you take the change of x over 2 and multiply it to y sub 0 plus 2 times y sub 1, 2 times y sub 2, and so on, up to 2 times y sub n minus 1, and then you add y sub n. And just to remind you, all the y's are just values of f at the n plus 1 points, x sub 0, x sub 1, up to x sub n, where x sub 0 is a and x sub n is b. And the difference between a and 2x values is the constant change of x, which is always b minus a divided by n. So as an example of using the trapezoidal rule, just as a reminder, the definite integral from a to b of f of x dx by the trapezoidal rule is approximately equal to the change of x divided by 2 times a summation y sub 0 plus 2 times y sub 1 and so on, up to 2 times y sub n minus 1 plus y sub n, where every single y value is found just by evaluating the function at particular x values, and all the x values begin with, in this case, a, and you can find the next x value in the list by just adding the change of x, where the change of x is a constant, b minus a over n. Let's go ahead and use that on this particular definite integral. Now, I need to start with an x value, in this case of 1. The final x value will be 4. And to determine what the change of x would be, I need to pick an n value. I can pick anything I like. So I'll pick, just out of the blue, pick 6. That means the change of x then would be 4 minus 1, b minus a over n, which would be 0.5. From that, I can then generate all the x values. Notice each one can be found from the previous one by just adding 0.5. You start at 1, you end at 4. And all the y values can be found by just evaluating the function, in this case x squared, at each of these x values. Now we just use the formula that the definite integral from 1 to 4 of x squared dx would be approximately equal to that particular product. And that is equal to 21.125. And that's close. That's close to the right answer. So the trapezoidal rule has many advantages, but it just so happens that there's another rule called Simpson's rule, which instead of using line segments that create trapezoids and using those areas to approximate our in particular definite integral, Simpson's rule uses parabolas instead. And it winds up being that it gives you the exact same amount of computation, but the error is actually a lot less when you use Simpson's rule when compared to the trapezoidal rule. And since each techniques basically use the exact same steps except for changing just a couple numbers, no one really uses trapezoidal rule. Almost everyone uses Simpson's rule. To give you an idea of how to go about generating this formula, it's going to be a little bit more complicated. Let's take a bunch of x values that are equally spaced out. Now, I'm only going to focus on 3. And to make it even easier, let's focus on the x values of 0, and then a small increase in that x value called h, and a small decrease. That gives us these 3 x values. 0 I didn't include. For these x values, just find out their corresponding y values. And trying to be kind of consistent with the formula you saw before, we'll call them y sub 0, y sub 1, and y sub 2. Now, through these points, there is a unique parabola that goes through them. I don't know what that parabola is, so I'll just call it P. But I'm assuming then that P at 0 would be y sub 1, P at h would be y sub 2, and P of negative h would then be y sub 0. Well, what we're after then is the area underneath that parabola. Notice the parabola and the function curves are very similar in the range from negative h to h. So I should expect that the area between the function and the x-axis and the parabola and the x-axis are very close. So here is the area then underneath that parabola. Just by doing the normal definite integral, we then evaluate the bounds and subtract to get that answer. We can then factor out the common factors of a third, a 2, well, not the 2, we'll leave the 2 there, but also the h. So we'll factor out an h and a third. That gives you that answer. Now, if we only knew what 2 times a h squared plus 6c was in terms of y sub 0, y sub 1, and y sub 2, we would have a really nice way to find the area of the parabola, underneath the parabola, and above this interval by looking only at the y values. Well, but if you remember, I said that the parabola evaluated at h would be y sub 2, and the parabola evaluated here at negative h would give you y sub 0. So just plugging things in, you get those two equations, which you could then add together to get that. So we now know what y sub 0 plus y sub 2 is. It's 2 times a times h squared plus 2 times c. Well, but we also know from the assumptions I've made that p of 0 is y sub 1. So that means then, just by plugging it in, that y sub 1 is c. If we then go back to the area underneath that parabola over the interval from negative h to h, we can rewrite that as h over 3 times the sum of 2a h squared plus 2c plus a 4c. From that, you can then see from what I've done above that that's actually equal to h over 3 times y sub 0 plus 4 times y sub 1 plus y sub 2. So let's use that previous result in order to generate Simpson's rule. As before, let's assume that f is a continuous function on the interval from a to b. And also, for simplicity's sake, let's assume the function is positive. That way, the definite integral just represents the area underneath the curve and above this particular interval. As before, let's go ahead and partition the interval from a to b into x sub 0, x sub 1, and so on up to x sub n, and assume that the change between every x value is exactly the same, to get n equally length subintervals, each whose length is b minus a divided by n. Also, though, unlike what I did with the trapezoidal rule, let's assume that n is even, because if it's not even, I won't be able to do all the steps I intend to do. Now, as before, define all the y values like we did before. But now, instead of looking at every subinterval, look at every two consecutive subintervals. Pair them up. So if you look at the first pair, the first and second subinterval, I can then form a parabola that fits them. And for that parabola, we know how to find the area, because the area only determined, or was only determined by the y values that were generated by looking at the three equally spaced x values. It didn't matter what the actual function was. And it doesn't also matter that before everything was at or near the x-axis, because I could easily translate the graph left and right, preserving the y values and not changing the area, of course. Do the same thing for the next two subintervals. That would be the second and the third. That would then give you another parabola. It would then give you another area. Basically, though, the form is exactly the same, because all I need is the three y values, y sub 2, y sub 3, and y sub 4, which correspond to the three equally spaced x values. Just do that for every pair and add them all up. So, if you want to approximate the value of the definite integral, just take the sum of all those different areas. And that's me writing it all down. Notice, though, that each part of that sum is a product, and every product has a common factor of the change of x over 3's. Just take all those out. And then notice that certain y values are actually added twice. Y sub 2 is added twice. Y sub 4 would be added twice, and so on. So if you add it up, you get this. And this looks a lot like the trapezoidal rule, doesn't it? In fact, the only difference between this and the trapezoidal rule is that in the trapezoidal rule, you divide by 2 in front. And the coefficients in front of the y's are either 1 or 2. Simpson's rule starts with a 1, then does 4, 2, 4, 2, 4, 2, 4, and then 1. Those will be the coefficients. That's the only difference between Simpson's rule and the trapezoidal rule. So let's go and do another numerical example. Just as a reminder, Simpson's rule is just a way to approximate the definite integral of a function that's continuous over the interval from a to b. It's given by a formula that looks a lot like the trapezoidal rule. The y values are just found by evaluating the function at certain particular x values, which form a partition of the interval from a to b, so that x sub 0 is a, x sub n is b, and the difference between any two consecutive x values is a constant change of x, which is given by b minus a over n. So doing that, let's go ahead and find or estimate the value of the definite integral from 1 to 4 of x squared dx. So we know the starting x value is 1. Let's just pick an n value to be 6 to be consistent with what you saw before with the trapezoidal rule so we can compare. Also, I'm picking n as 6 because to use Simpson's rule, the end must be even. There's no such limitation on the trapezoidal rule. But for Simpson's rule, because of the pairing up of the subintervals, the end must be even. That means that the change of x has got to be 0.5. That then gives us the exact same table of values of x values and y values. No, so far nothing's been different. But the way we use these x values and y values does change because the rule's different. This time, the definite integral from 1 to 4 of x squared dx is approximated by the change of x, which is 0.5, divided by 3, and then notice you have a certain sum of products. You have 1 times the first y value, then 4 times the second, then 2 times the third, and so on. That then oscillates 4 times something, 2 times something, 4 times something, 2 times something, till eventually you end 4 times something, and then lastly, you add the very last y value. If you do that arithmetic, you get 21. So you would say then the definite integral of x squared, when you integrate it with respect to x, as x goes from 0 to 4, is approximately 21. And you may wonder then, what is the error? Like, how close are we? So we got 2 answers. The trapezoidal rule got us 21.125. This got us 21. Well, it winds up being that in this case, Simpson's rule actually gave us the exact answer. There's no error at all. And there's a good reason for it, based upon a theorem about the error term, which is what we'll talk about next. Whenever you have an approximation, you'd like to know what is the error between your approximation and the true value, which is difficult because we don't know what the true value is. That's the whole point. But with error analysis, we can use much more advanced calculus in order to estimate an upper bound on it. It goes like this in our case. If the function's second derivative is continuous and m is any upper bound on the values of the absolute value of the second derivative on the closed interval from a to b, then the error in the trapezoidal approximation of the integral of f from a to b from using n steps satisfies the inequality that the absolute value of this error is bounded by the bound m times the difference in the x values, b minus a cubed, divided by 12 times n squared. Now, why is this good? Well, it says, though, think about what the different things could be. If n grows, then the denominator gets incredibly large. The numerator, though, is constant because the m is just a single upper bound for the values of the second derivative in absolute value. That upper bound doesn't change as n changes. B minus a doesn't change. So this says then that as n grows, the error is driven to 0. And it gives you a measurement on just how big of an error would be. You can get the same kind of result, but much, much stronger for Simpson's rule. It says that if the fourth derivative is continuous and m is any upper bound for the values of the absolute value of the fourth derivative on that interval, then the error in using Simpson's rule to approximate the integral of f from a to b using n steps where n is even satisfies the inequality that the absolute value of the error is no more than that bound m times b minus a to the 5th power all over 180, and here's the kicker, times n to the 4th. Now notice that if n grows, that denominator grows really fast. So that means that if n becomes just not so large, like say 4, 5, 6, that this error term for Simpson's rule is really small. Especially if the difference between b and a is also small. Because then if b and a, if that difference is small, when you take it to the 5th power, that makes it even become smaller. So Simpson's rule is definitely at a better approximation compared to the trapezoidal rule. And for that reason, no one really uses the trapezoidal rule. Everyone uses Simpson's rule. So I'll go about using that formula once to show you an upper bound for the error in estimating this particular definite integral when we use Simpson's rule where n is 4. Now, of course, we know the exact answer. That's not the point. I want to go and just show you ahead of time how good Simpson's rule would be if you want to approximate that definite integral. Well, to do so, I know that the function I'm using is the cosine of x. Simpson's rule requires that I take the first, second, third, fourth derivative. So I need to know the first derivative, which of course would be negative the sine of x. I would need the second derivative, which of course would be negative cosine of x. I would need the third derivative, which would then be the sine of x. And the fourth derivative, we're right back where we were. We're right back to the cosine of x. So I need to know then what could be the maximum value. What's the maximum value of the function, which is the fourth derivative, evaluated at x, but where x can vary over the interval from 0 to a half? Well, I could find that out. I could actually figure that out, mainly because I know that the cosine over this interval is decreasing the entire time. So of course, the maximum value of the cosine function, in this case, since it's decreasing, is at the very first x value. So that would be 1. So the maximum value is 1. So I can use that as my m, as I'm certainly sure that whatever it is, it's less than or equal to that 1. So that would then mean that the error when using Simpson's rule in absolute value, because I don't know if my estimate is an underestimate or an overestimate, would then be no more than the bound m times b minus a to the fifth power all over 180 times n to the fourth power. But in this case, I know what that is. M is 1. B minus a, that's a half to the fifth power. That's all over 180. And n in this case is 4 to the... I have to raise that to the fourth power. And that's it. The error is less than that. And if you were to crank that out, that's incredibly small. Incredibly small. So notice by using Simpson's rule just where n is 4, we get a really close approximation to this particular definite integral. And that gives you a basic introduction to numerical methods to approximate definite integrals. Of course, there's many other techniques beyond this, but this is more than enough for what you'll need for Calc 1, 2, or even 3.